Okay, I think the Duke can announce the session now, and we can start. Okay, ready? Okay, congrats for the Duke. Okay, hello everyone again, and thank you for coming to this talk. This is my second talk for today, and we're going to speak about the security architecture of the Java platform. How many of you have done some security programming for the JVM? Okay, 1, 2, or 3 people. How many of you know what a security manager is in Java? Security manager. Okay, 4 or 5 people. Okay, so in this talk, basically, we'll go through the history of the Java security model, and we'll discuss basically how this model evolved up to JDK 9, and basically what you as Java developers need to take into account when you do Java programming or when you develop your own libraries for the Java platform, considering that security model. So first of all, a few short words about me, who hasn't attended my previous talk. My name is Martin. I have my own company called Coffee Cup Consulting. I'm also one of the guys that organizes the events of the Bulgarian Java user group. We have our own conference called JPrime, which is in May. And you can follow me on Twitter. I tweet entirely about Java. I also have a book about RabbitMQ called Learning RabbitMQ. It was published just recently. So if anyone is interested in RabbitMQ, you can find me after the session and we can go into more discussions. So in this talk, basically, we'll start discussing what's the security model, security sandbox model of the JVM. Then we'll discuss briefly what are the supporting security APIs in the JDK. And finally, we'll see some best practices that you should consider when you develop your Java applications, considering that security model. So when it all started, essentially, companies have always tried to protect their assets. When you switch jobs or start a new company, in a new company, they always give you, or in most cases, they give you a security policy that you can go through and read how you should protect the assets of that company, how you should protect the software of the company, and so on and so forth. And for that reason, companies traditionally have deployed different types of firewalls or intrusion protection systems in their networks. However, with the introduction of various technologies that allow you to execute source code directly from the browser, such as Microsoft Silverlight, Java applets, Flash, and other types of technologies, basically a whole new range of security risks arises on the horizon. And the idea of the Java security sandbox model is to deal especially with that kind of problems, the execution of source code from a managed environment, which is the browser itself as well. And the goal basically is to allow untrusted code from third-party sources, such as applets, to be executed safely in an environment such as your own PC. In Java 1.0, when it all started, essentially the sandbox model was pretty simple. You had the JVM running inside your browser, and you also had various Java applets which were executed from different locations in your browser. The source code of the JVM, with all of its classes, was treated as trusted, meaning that it can do everything with your system. Create files, open sockets, and so on and so forth. And Java applets were treated as untrusted, meaning that strict permissions were applying to what they can do on a target machine. And basically, code was divided in 2 domains, trusted and untrusted. Trusted was only the JVM source code, and untrusted was the one from applets. However, this was really not a very flexible model. So in JDK 1.1, this model was a bit tuned, and the possibility to sign applets was introduced. Applet signing means that basically you trust a certain set of applets, and you give them the same permissions as the JVM. So basically now the applets could be either trusted or untrusted. And the process of basically signing an applet is pretty straightforward. Nowadays, no one will probably have to develop applets, but still this is a good overview of how you can do it. You compile the applet, create a jar file, generate a pair of public-private keys, import the certificates for these keys in trusted certificates, create a policy file for those applets, and execute them. In JDK 1.2, however, this model was still kind of not very flexible, so they decided to change it entirely. And this is when the so-called security manager was introduced, which is basically used up to the current versions of the JDK. So basically, the JDK 1.2 version introduced the security sandbox model as it is up to date. And it basically provided you the ability to specify security permissions in a so-called security.policy file, which by default comes with the installation of the JDK. So it's a text file that provides a domain-specific language where you can specify what are the permissions for a given source code. So for example, you have an applet which is javantura.com/demo applet, and you want to apply certain permissions on that location of where the applet is loaded from. Then you put the location as a grant code base, then the location of that applet, and you specify the permissions that you grant to this applet. In that particular case, the standard Java permissions have three distinct parts. The first one is the type of the permission. In that particular case, it's a file permission. The second is the target to where that permission applies. And the third one is the action. In that particular case, I give the applet the permission to delete the C Windows folder. Also, another API was introduced, which is the access controller, which is essentially a bit of a newer API. And the security manager behind the scenes uses access controller to check permissions. We'll go into the details of how permission checking is being done in a few slides. So now, with JDK 1.2, the security model becomes more code-centric. You don't have anymore the notion of trusted or untrusted code. And access control decisions are typically specified in that security policy file. However, there is something new introduced which is called protection domain. And the protection domain basically is determined by the security policy file. And we have two types of protection domains. The system protection domain, which is essentially the classes of the JVM, and the application protection domain, which are the classes of your application and the libraries that you use. And if you want to get the protection domain from any class in your application, you can just call .getClass.getProtectionDomain. domain. From that protection domain, you can get the location of where that class is loaded from, also, and the set of permissions that apply to that particular class. Now, one specific thing about Java permissions is that one permission can imply another permission. For example, if I specify that I'm able to delete the C Windows folder, this also implies that I can delete the C Windows System32 folder. So this is one important property of permissions. And another important property is that also code bases imply each other. For example, if I specify that I apply those permissions to everything that's loaded from javantura.com, this automatically means that the same set of permissions applies to everything that is loaded from javantura.com/demo applet. This is another important property of permissions. Now, another thing is that since basically the execution of a source code can pass through classes that are loaded from different class loaders. And typically, in the Java permission model, a protection domain is set by the class loader that loads a particular class. This means that you need to somehow determine what is the active set of permissions for the currently executing source code. This is determined basically when the JVM scans through the stack trace of all the invocations that reach to that point in the source code where you need to check for permissions. And each of those places in the stack trace needs to have the particular permission. However, there are certain scenarios where when your source code may pass through different protection domains. For example, if you have a WAR file in a Java application server, the WAR file has one application domain, and this is the location of where that WAR file is loaded from. And the application server has another protection domain, which typically is the current file system that executes the application server. And now comes the question, how do we determine the set of permissions of source code that's executed by the WAR file? And the set of permissions is basically determined simply as the intersection of protection domains through which the code passes. In that particular case, this is the intersection of the protection domain of the WAR file and the protection domain of the application server. In JDK 1.3 and 1.4, the security model remains the same. However, something new is introduced called JAS. Does anyone know what JAS is? And yes, a couple of people. So basically, JAS is, or the so-called Java Authentication and Authorization Service, provides the ability to not only specify permissions based on the location of where source code is loaded from, but also which user executes the source code. So far, before version 1.3, the Java security model didn't allow or provide out of the box the possibility to specify who is executing the source code, only from where that source code is executed. And in version 1.3, the security policy file was extended with the ability to specify also the user that is executing the source code. In that particular case, I specify that the current user, which is some LDAP principal, this specifies essentially an LDAP entity, has the permission to delete the C Windows folder. I can also specify a location, so I can combine locations with users. And out of the box, just provides different modules that allow me to specify, for example, users in an LDAP system, in a relational database, and so on and so forth. So JAS is essentially divided into two parts, authentication and authorization. And in fact, JAS not only extends the security model with role-based permissions, but it provides also the ability to specify pluggable authentication. For example, you can specify a GUI window in your application that authenticates the user, and you can have a different authorization scheme which is specified by the security policy file in Java. Now, the protection domain of a class is also extended. Currently, it supported only the ability to get where is the code loaded from and what is the set of permissions. But now, from the protection domain, you can get a third thing, and that's who is the user or the subject that owns the currently executing source code. And in fact, it's the authentication component of JAS that's independent, essentially. As we said, it provides the ability to load source code pluggably, but it's the authorization component, as we saw in a few slides, that extends the syntax of the security policy file. So you can think of it as two distinct parts. And here is a set of core classes that's provided by JAS. First, you have the user, which is an instance of JavaX security auth subject. A user has one or more principals, which are the characteristics of the authenticated user. A principal can be an email address, a username, and so on and so forth. And in order to log in a user in your application, you need to have a login module that specifies the logic of how your user should authenticate to the system. By default, the JDK provides several standard login modules, such as LDAP login module. It also provides Kerberos login module for authenticating using the operating system, for example, if you're using Windows. And also, in order to be able to create login modules, you have the login context, basically, that works with these login modules, and is the first entry point towards using JAS. Now, in JAS, basically, you can combine different authentication models. For example, you can authenticate users both against an LDAP and a relational database. And you can combine special rules on how you need to authenticate using different systems. Now, to summarize up to JDK 1.4, we have the following flow for permission checking. Your application starts up, and an active policy file is set. If you don't have by default a security manager installed, which is the case for most Java applications, you don't have any permission checking. However, if you set a security manager with system.setSecurityManager, as most application servers, OSGI runtimes, and other managed environments do, then permission checking is enabled. Also at runtime, the active policy file is set by calling policy.setPolicy, which brings up the permissions, the active permissions in your JVM. This is the first step. The second step is that the classes of your application must be loaded by a class loader, and this is when bytecode verification is done to check whether your bytecode is valid according to the Java language specification. And then this is when exactly the protection domain of the classes that are loaded is set, along with the location of where the classes are loaded, the set of permissions, and the set of just principals. The third step is that your application invokes some system code. For example, it tries to write to the file system or open a socket. And this is when the JVM calls a security manager.check permission to see whether your application has the ability to do whatever it likes to do. By default, the JVM does permission checking for example, whether you are allowed to do reflection, whether you're allowed to have file permissions, and so on and so forth. So this is basically something that's done behind the scenes and you don't see it. This is also something that application servers typically do when they execute a WAR file or JVM in the browser when it loads applets does. So they also do permission checking. And permission checking is done pretty much similar to that piece of code. You create some type of permission. In that particular case, I create a socket permission, which applies for the javantura.com site for ports between 8,000 and 9,000. The actions to which that permission applies are connect and accept. Then I get the currently installed security manager by calling system.getSecurityManager. And if I don't run a security manager, I skip permission checking. But however, if I have security manager, I call sm.checkPermission and by passing this permission. What the JVM does at that point, it traverses the call stack of where this is called from. And if all of the frames in that stack have the permission to open the socket with that particular parameters, then I have a permission granted. Otherwise, I get a security exception. The fourth step is essentially the application code can also do permission checking using a security manager or an access controller. And this is typically the case with basically application servers. For example, when you load a kind of WAR file in your application server, the application server can do permission checking pretty much similar to what JVM does. And you can also use the access controller class in your application server. And the difference between a security manager and an access controller is, first of all, you don't need to have a security manager installed because the methods in the access controller class are static. And this means that even if you don't have a security manager installed, you still force permission checking at the level of the application. And this is basically equivalent to the previous example we saw, but with using access controller instead of security manager. And application code can also decide to do privileged execution of source code. This is the case, for example, when, let's give an example with a WAR file. A WAR file wants to use the logging service provided by the application server, and it wants to write to the file system. However, by default, we have a security policy for that WAR file that doesn't allow it to write to the file system. And when that WAR file is executed in the application server, we get a security exception. So the application server needs to somehow work around this policy that applies to WAR files in order to allow certain pieces of that WAR file to write to the log. And the reason we can do that is by doing privilege escalation. And this can be done, for example, by calling access controller.doPrivileged and inside specifying the action that needs to be executed. This piece of code is found in a lot of Java application servers. And what it does essentially is that it skips permission checking for the stack trace where this is executed. This means that if this is executed in an application server, the permissions for the WAR file are simply skipped. And the active set of permissions is the one for the application server. You can also do other things, such as changing the currently active user that's executing the source code by calling subject.doas and specifying a just subject. Or you can do both. You can change the user and execute your source code in a privileged mode. And the security model typically defined by the Java Security Manager is customizable. What we've seen so far is the default way how the JVM does permission checking. However, in certain types of environments, we have custom implementation of a security manager. One particular case is, for example, Oracle JVM. Inside of Oracle database, we have a security manager that runs in the environment that executes Java stored procedures. And that security manager is customized to do permission checking based on permissions specified in a relational database table. And this is essentially a custom implementation of a Java Security Manager. Moving on with JDK 1.5 and 1.6, no radical changes in that security model. It still remains the same. There are some enhancements made, for example, such as LDAP support introduced for JAS. This happened in version 1.5. In 1.7 and 1.8, still no major enhancements to that security sandbox model. For example, one thing was added, such as the ability to specify only a subset of permissions for access controller.do privileged, meaning that you can do privileged execution only against the subset of permissions that you specify explicitly. In JDK 1.9, what we expect, in JDK 1.9, as most of you know, a modular system for Java is targeted. Not fully modular system as Milen described, but a modular in terms of the JDK. And with the introduction of Jigsaw, essentially the JDK code base is split into a form of modules. And what this implies to the Java security model is that now each separate module of the JDK can have its own protection domain and its own certain location from the file system where it is loaded from. So far, the JDK was a big monolith with all classes in one place, and that's why we had the notion of system code. All classes in the JDK had the permission to do whatever was given to the JVM classes. However, with the introduction of the Jigsaw module system, now you can specify permissions based on certain Jigsaw modules. For example, you can have one set of permissions for Java util logging, and another set of permissions for, let's say, Corba, which no one uses, for example. So essentially, the security model in terms of the module system introduced in JDK 1.9 remains the same. However, there are some internal changes done by Oracle, and this is to provide some more permissions to certain modules and to restrict permissions to other modules in the module system. So you might expect that with JDK 1.9, there will be certain changes to what certain classes in the JVM can do by default. But really no changes to the security model. Yeah, this is what we already mentioned. Now, if we look on the other side of the coin, we have the Java Security Sandbox model. However, this is really not sufficient for most applications that need to do some kind of certificate management or to do some kind of encryption and so on and so forth. And for that reason, the JDK provides a number of useful utilities that you can use in your applications. And this include, for example, the Java cryptography architecture, which provides you with utilities to encrypt or decrypt certain pieces of information. You have the PKI infrastructure utilities, which allow you to communicate with the certificate authority or to create your own certificate authority. You have the secure socket extension, which is the SSL version of standard Java sockets. You have an alternative of Java Secure Socket Extension, which is Java GSS API. Java GSS API essentially provides a way between a client and a server to communicate by means of exchanging security token. And last but not least, you have the Java Simple Authentication and Security layer, which basically provides a mechanism for exchanging of authentication information. For example, you have a client, and the client asks the server, hey, can I authenticate against an email, or shall I use a username? And the server responds, yeah, you can use your email address to authenticate against me. So the SSL API essentially provides you with a protocol that allows you to establish negotiation between a client and a server on how you need to authenticate. And essentially, this is the major set of APIs provided by the JDK. The JDK itself doesn't provide, for example, concrete algorithms for encryption or decryption. It provides just the API that you need to use in order to implement your own algorithms. And the standard provider that many applications use is the Bouncy Castle library. Has someone used Bouncy Castle? A couple of people? Yeah, it provides a lot of algorithms that you can use to provide security in your application. And the last part is basically now considering this security model and the supporting APIs in the JDK to consider also several best practices that you can apply when you design your applications. First thing is that most of the guidelines that you have in security are really not bound to Java. There are some general practices, such as, for example, you need to properly sanitize input. You make sure that you use just safe types. The proper access modifiers are specified, and so on and so forth. However, there are certain guidelines that apply particularly to the JVM. And one of them is, for example, to respect the security manager. This means that essentially if you are designing a Java library, you need to design that library in such a way that you take into consideration the fact that this library can be used in a managed environment such as OSGI or Java EE application server. There are many examples of Java libraries that are being developed without the idea that there exists a security manager. And when you try to use that library in a managed environment, you get interesting effects. For example, I had a while ago the case when I wanted to use the JSON library in an OSGI bundle. And the JSON library didn't provide me with any way that it used the security manager inside of the library. So what I hit was the JSON library essentially tried to use reflective calls, which are disallowed to bundles. And what I needed to do was to provide a way to do privilege escalation inside the JSON library. So I had to patch the library so that it was aware that it can run in an environment with a security manager installed. And this is the case typically with a lot of Java libraries. It's not only JSON. So this is one thing that you have to take into consideration. The other thing is to grant minimal permissions to code. There are many cases where you get a security exception and you try to modify the permission file and you specify all permissions for the source code, which effectively is really not a good practice. So basically you need to specify only the minimal set of permissions that your application needs to do its job. Also, you need to take care that you don't show stack traces to the user. This in the Java world is particularly famous when you see many applications throwing at you 200 lines of stack trace. So this is really not a good practice. And that's it. Thank you. I'm not sure if we have time for questions. 1 minute. Okay, if there are any questions, I think there is 1 minute. If not, then thanks.